talk about atomic spectroscopy. So, just like with the UV-Vis molecular spectroscopy that we talked about, we can measure the presence of atoms in a variety of ways. We can look at emission, where you're having an excited state, photons emitted when you have an atom moving from an excited state to a ground state. You can do it by absorption, where you have atoms in a ground state moving into the excited state. And you can do this by measuring fluorescence, where you first have an excitation event, and then you're measuring the photons that are emitted. Alright, so the first geometry that we're going to talk about is atomic emission. So basically what you have is you have a flame that's where you have fuel, which is usually acetylene, and an oxidant, which is often air, but it could be nitrous oxide, coming in and generating a flame. And you have your sample that's aerosolized or nebulized and atomized and going into the flame. And so for emission spectroscopy, you have the flame, some population in the flame, because it's 2,500 degrees Kelvin. Some population of the atoms that are in the flame are going to be in the excited state. So those atoms will emit photons when they return to ground state at a element-specific and transition-specific wavelength that you can tune your monochromator to look for, and then detect those photons. I keep wanting to say X-rays because that's what I think about all the time. Anyways, basically your mono is going to select a single emission that is going to be looking specifically for the single emission energy, and it also reduces the contribution of the flame that gets to the detector. So basically, to review, the sample is nebulized and atomized. Some portion of the sample is thermally excited in the flame, and then the sample emits element-specific wavelengths when it returns to the ground state. Okay, emission measurements like this in this geometry are very sensitive to temperature, because temperature is sort of the main factor in determining what portion of the population is going to be in an excited state relative to the ground state. And that's described by Boltzmann's distribution. So you can also look at atomic absorption. And so basically you would have something like a hollow cathode lamp, which generates specific element-specific wavelengths, and we'll talk about how that does that in a second. And then you have the same way of getting the sample into the flame, where it's atomized, and then the photons interact and absorb, and interact with the atoms that are in the flame. Some of them are absorbed, and then you measure what's left. So same thing, where you're looking at the energy that's being produced by the hollow cathode lamp, that's the energy that your mono is going to be tuned to, and you're just looking at a difference, like how much is there before and after, and then that's what you're detecting. You can also use a chopper to eliminate the contribution of the flame. So basically, sometimes if you use the chopper to say, sometimes you get to look at all the excited. Sometimes you're going to have some that's taken away by the atoms in the flame, and sometimes you're just going to be looking at the contribution of the flame. So that can also help you increase your sensitivity. So let's talk about how a cathode ray lamp works. Basically, what you have is a cathode, a hollow cavity cathode, and an anode. And in this tube, you have mostly a vacuum, but you have the vapor of the element to be analyzed at 1 to 5 torr, so very low pressure. And then this is a window that allows the light that's produced to escape. So you start it up by applying a 500 volt potential, which causes gas ionization. The cations go to the cathode and crash into the cathode. And then you maintain a 2 to 30 milliamp current. Then you have the electrons. So the cations went to the cathode. The electrons strike the other gas molecules on their way to the anode, which results in those atoms getting excited, or the gas molecules or atoms getting excited, and then you have emission, and those emitted photons go through the window and then can interact with the sample atoms in the flame. So these produce extremely narrow bandwidth radiation, much better than you can produce with the monochromator. So you're basically only getting the energy for the specific element. The third geometry that we want to talk about is you can excite using a laser or a hollow cathode tube, and that excites the atoms. You tune it so that it excites the specific atoms in the flame, and then at 90 degrees geometry, so this is in 3D space, you would then have the monochromator tuned for the emission energies that you wanted to measure, and then you detect those. So it's just like the UV-Vis geometry. So we've talked about introducing the sample by flame. You can also do it using a graphite furnace, which sort of looks like, and the geometry sort of looks like this. It's a tube that you can slide your sample into, and then the light comes in the opposite direction. And there's some benefits to doing it that way. So with a flame, the detection limit is 10 to 1,000 ppb. With the graphite furnace, it's much lower. It's 1 to 0.1 ppb. So the flame is faster and easier, but it requires much more sample, 1 to 2 milliliters versus 1 to 100 microliters. And both of these are kept at around 2,500 degrees Kelvin. So you can just substitute a graphite furnace in for the atomic absorption geometry. So let's talk briefly about what can go wrong. And what can go wrong basically with this type of measurement is interferences. And so those come in 3 flavors. So you can have spectral interferences where you have overlap of emission lines or absorption by other elements that are in your sample or by the flame. So this would usually result in falsely high measurements. So you're going to measure that there's more of your element of interest in the sample than there actually is. You can also have chemical reactions, chemical interferences. Basically, you have chemical reactions that decrease the amount of analyte that's atomized, and that gives you falsely low readings, although you can use releasing reagents to try to combat that issue. The third is that you could have ionization interferences, where you have an element that can become ionized, and that's not what you want, because you're looking, they have different energy levels. The whole atom and an ionized atom have different energy levels, so you're not going to be looking at the right energy if you have a lot of this ionized, large population of ionized atom of whatever your sample is. This is especially true for the alkali metals because they have such low ionization energies, but it can definitely affect other elements at high temperature. So this would give you falsely low readings, and you can use an ionization suppressor. In order to combat all of these interferences, you can also use a standard addition method, which we talked about earlier on. So let's briefly go back and revisit detection limits. So detection limits, basically, I listed several techniques. We haven't talked about either of the ICP techniques so far, but that's coming right up right up around the bend. So I just looked it up for the first row transition metals. So basically, flame AA so this is listed in order of least sensitive to most sensitive. So flame AA, you're in the tens of ppb range, from 70 to 0.0 to 0.5 for the first row transition metals. ICP OES is the next most most sensitive, and you're in the low ppb range right there with 3 to 0.2. The graphite furnace AA is better yet, with less than ppb detection limits, and the ICP-MS is actually much better. You can get down below 5 parts per trillion, so that's way lower than any of the other methods. And so the ICP-MS is actually the instrument of choice for research grade trace metals work.